Hello everyone, and thank you for joining us today. Today's topic is factory acceptance test of power and distribution transformers using ICMsystem. My name is Sebastian Dreher, and I'm development engineer with Power Diagnostics by Megger. I'm a moderator for today's webinar and will provide technical support for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in a box highlighted in red. I'll read the questions out during the Q&A segment at the end of the webinar. All webinar attendees will receive an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to the video recording if you like to watch it again or share it with your colleagues. Please remember that you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Daniel Hering, Product Manager with Power Diagnostics. Also, to assist with the question and answer session, we will have one additional panelist joining us today, and that's Markus Fockenberg, Senior Development Engineer with Power Diagnostics. Okay, let's go ahead and get started. Thank you for joining us today, Daniel.
Yeah, I'm Daniel Hering, presenting today the webinar Factory Acceptance Test on Power and Distribution Transformers using the ICMsystem. As an introductory part of this webinar, we will go through the standards defining the factory acceptance test procedures for power and distribution transformers and discuss about the various requirements for standard compliant PD testing. We will continue with a short explanation covering partial discharges, the signals they create, and how these signals behave in a transformer. Afterwards, this webinar will continue with its main topics, namely the ICMsystem and how factory acceptance testing of transformers is done with the ICMsystem. As you will see, at least I hope you will, a successful factory acceptance test is basically straightforward. Nonetheless, in the case of a failed factory acceptance test, the last 2 sections will give examples how the ICMsystem provides further options to successfully identify and locate the issue, enabling the user to fix the problem. So coming to the introduction. Transformers are vital parts of every modern power distribution network. From a design and manufacturing view, they are a complex structure of mixed materials and components. This led to the introduction of extensive factory acceptance test requirements, short FAT, for transformers in general. Therefore, numerous standards address FATs of power and distribution transformers. The various standards distinguish via ratings and between dry type and oil, or better, liquid immersed transformers. So here we will now list a few of the most relevant standards which address transformer factory acceptance testing in one way or another. First, the standards defined by the IEC. 2 IEC standards have to be mentioned in special. First of all, the IEC 6060. The IEC 6060 defines basic requirements for voltage measurements on all types of equipment, making it a horizontal standard. The second standard to mention is the IEC 6763. While the IEC 6763 is per definition referring to power transformers, which are usually oil immersed due to the required ratings, it can be considered as a quasi-horizontal standard when it comes to partial discharge testing of transformers. This is due to the fact that it was one of the first standards for transformers mentioning PD testing. Therefore, other standards, even the ones focused on dry type transformers, are often referencing back to the IEC 6763. The second half consists of the IEEE standards. The IEEE gathered the standards relevant for transformers under the C57. Since you are most likely asking yourself why there are some standards printed in bold, the standards in bold are listing the mandatory tests which have to be performed during a transformer factory acceptance test. The older version of the mentioned standards, if they were existing during the time, refer mostly to radio influence voltage testing, short RIV. Why RIV testing? In the 1913s, it was a critical problem that high voltage equipment sometimes seemed to interfere with radio signals. These interferences have been tracked back to be created by corona, so discharges into air. And RIV testing has been introduced as a solution to detect possible corona problems before putting equipment into operation. Due to this approach, RIV testing focuses on problems HV equipment could create for radio signals. RIV testing was not intended to be a diagnostic tool. With ongoing research, partial discharge measurements were found to give detailed information about the complete insulation system of the transformers as a diagnostic tool, not only giving a simple pass or fail criteria. Furthermore, PD testing also covers the main reason to do RIV measurements, namely creation of radio disturbances due to due to the corona. Therefore, PD measurements more and more supersede RIV measurements. Nonetheless, RIV measurements are still very common in the North American area and the Asian room. So, coming now to the standards referring to PD measurements. The first and most important one to mention is the IEC 60270. It defines the common partial discharge testing method using a coupling capacitor together with the measuring impedance as measurement circuit. This kind of IEC 60270 compliant PD testing is called conventional method. So, since all kinds of transformer factory acceptance tests are done using this conventional methods, fulfilling the IEC 60270 is a basic requirement for the PD measurement during a transformer factory acceptance test. On the opposite, the IEC 62478 focuses on non-conventional PD testing, so either acoustic or electric measurements with antenna-type sensors and or varying frequency ranges, namely UHF or similar. The IEEE C57.113 is based on the preceding standard for RIV testing, namely the NEMA 107, but also referencing the IEC 6270, the IEC 62763, and IEEE 454/1973, which is additional standard part of the IEEE regime. And again, I would like to emphasize there are numerous additional standards which are not mentioned here, since the development in PD testing, especially when it comes to DC testing, is progressing fast. Now let's take a look at the IEC 60270. While the IEC 60270 with its amendment from 2015 has of course a detailed list of requirements covering the detector, calibrator, and so on, which manufacturers of equipment for measuring partial discharges have to take care of, we will focus on the restraints that have to be considered when you stand in front of a transformer and have to do an acceptance test. These are then the allowed frequencies for measurements. First, wideband measurements. Wideband measurements according to IEC 60270 are measurements with a bandwidth between 100 and 900 kilohertz. Together with the bandwidth, the IEC also limits the allowed lower and upper corner frequency. The lower corner frequency has to be between 30 and 100 kilohertz, and the upper cutoff should not exceed 1 megahertz. The second option are narrowband measurements. Here, the bandwidth has to be between 9 and 30 kilohertz, and the frequency has to be between 50 kilohertz and 1 megahertz. However, narrowband measurements have some serious disadvantages. Narrowband measurements suffer under strong oscillations created by the according bandpass filters. These oscillations make it nearly impossible to distinguish the polarity of a PD pulse correct. Furthermore, the longer decay time due to these oscillations limits the possible time resolution for repetitive PD pulses. Therefore, wideband measurements are heavily preferred for PD testing. With the ongoing webinar, we simply have to keep in mind factory acceptance testing of transformers has to be done in the frequency range below 1 megahertz. So after giving the short overview over the normatives references here, we will now continue with the question, where exactly is PD testing now part of a transformer factory acceptance test? So PD testing is part of the induced voltage test, either in combination with the withstand test or as a standalone induced voltage PD test, often referred to as IVPD. According to the IEC 6763, PD testing is mandatory for power transformers with a maximum voltage above 72.5 kV, and for transformers below this 72.5 kV, it has to be done in agreement with the customer, between customer and manufacturer, or if the agreement looks different, it doesn't have to be done. PD testing for dry type transformer, according to the IEC 67.3/11, is mandatory for all dry type transformers covered by the IEC 67.6/11 with a maximum voltage above 3.6 kV. The dry type transformer falling under the regime of the IEC 67.3/11 are all transformers with a maximum voltage below 36 kilovolts and a power rating above 1 kVA for single-phase transformers or 5 kVA for three-phase transformers. On the other hand, let's take a look at FATs done under the regime of the IEEE. While within the IEEE regime, PD testing is mandatory for all Class 2 power transformers with a nominal voltage between 115 kV and 765 kV. PD testing is not required for oil-filled Class 1 power and distribution transformer. A Class 1 power transformer is any transformer with a nominal voltage smaller or equal to 69 kV. A distribution transformer is usually any transformer with a rating between 5 and 500 kVA. For dry-type transformers, PD testing is mandatory for any transformer above 1.2 kV with solid cast and/or cast resin encapsulated windings. A specialty of the IEEE standards is the fact that PD testing is often still equated with RIV testing. So this slide shows the voltage curve that has to be applied for doing PD testing for oil immersed transformers. First, the voltage has to be raised to 1.5 times the maximum voltage for 5 minutes, then to the enhanced level, and then it has to be kept at 1.5 times the maximum voltage for 1 hour, with a value recorded every 5 minutes. The voltage is applied with an elevated frequency to avoid coarse saturation at the elevated voltages. Also, the elevated frequency shortens the time the enhanced voltage level has to be kept. 3 different requirements exist here. First, the enhanced voltage level duration according to the IEC 67.3 for any transformer with a maximum rating below the 800 kV. Here it's again this written formula, but no less than 15 seconds. For any transformer above this 800 kV maximum voltage, it's this formula, but no less than 75 seconds. The third option for this duration is according to the IEEE C57-113, simply 7,200 cycles, independent of the frequency. So the IEC 67.3 requires PD measurements on all bushings above 72.5 kV up to 6 bushings maximum, usually done by using the test step. The induced voltage PD test is passed when the voltage did not collapse over the complete sequence, and the following criteria for the 1 hour period are met. The acceptance limit, depending on the standards on agreements, is in a range of 250 picocoulombs. The noise floor has to be below 50 picocoulombs. And during the 1 hour measurement, the PD level shall not increase by more than 50 picocoulombs and no rising trends, respective Sudden egress in the last 20 minutes shall occur, otherwise the measurement has to be extended by 1 hour. One remark: beyond the required 6 bushings to comply with the standard, measuring additional available decoupling points, for instance neutral or tertiary windings, may give valuable information in case of a failed PD test. The second remark is regarding the acceptance limit here. 250 picocoulombs is stated by the IEC 60763. However, another common acceptance criteria is 500 picocoulombs as a limit for the enhanced voltage level, and then 300 picocoulombs for the 1 hour duration. Compared with the requirements for doing PD measurements on power transformers, PD testing on distribution transformers or dry type transformers is less complicated. For instance, only the 3 HV windings are measured. Due to the lower voltages, windings of distribution transformers often don't have dedicated test tabs. So PD testing of distribution transformers is done usually using a coupling capacitor. Also, the test sequence is much shorter. However, the acceptance limit of 10 picocoulombs is over a factor 20 stricter compared to oil-immersed transformers. One remark here: the IEEE refers to a length of 5 minutes for the first step and for power transformers. It refers to a period long enough to ensure inception of PD, a possible PD within the transformers, with a recommended minimum of 10 minutes. However, experiments have shown that even these 10 minutes may not be sufficient, and consider longer periods of 15 minutes or more. So when we take this into account, taking a look at dry type transformers, we have only 180 seconds testing time. So the 180 seconds testing time may not be sufficient to detect PD reliable. After having laid out the typical PD testing procedures, we will now give a short overview of what partial discharges in transformers are and which signals they radiate. Partial discharge is a breakdown of a small area of the overall insulation. To be more precise, partial discharge is the breakdown of the local electrical field within an imperfection of the insulation due to an electron avalanche. This electron avalanche generates 3 different measurable signals: a local displacement current pulse, electromagnetic pulses, and acoustic signals. At the origin, the local displacement current pulse has a rise time in a range of 1 nanosecond for nitrogen. This translates into 350 megahertz bandwidth maximum. Due to the RLC network of the transformer, the current pulse is translated into a voltage pulse on its way to the measuring terminals. And it's suffering under attenuation, dispersion, reflections, and filtering. So only a reduced frequency band reaches the detector. Especially, it's important to mention that these effects affect high-frequency signals stronger than low-frequency signals. Despite the effects mentioned before, the signal stays up to some limits in correlation with the real discharge value at the origin. However, failures within the winding, the deviation between real and measured charge is known to be up to 50%. Due to this known deviation, it's also then called apparent charge. The mentioned electron avalanche causes an electromagnetic pulse, which is radiated in all directions from its origin. While discharges in nitrogen go up to 350 megahertz, discharges in oil or solid materials can also show frequency components above 350 megahertz. Such UHF signals can be decoupled by UHF antennas. However, UHF signals cannot be correlated with the amount of discharge at its origin, so no calibration in terms of picocoulomb is applicable, since the signal strength strongly depends on the location of the antenna and the travel path of the electromagnetic pulse through the transformer tank. Last but not least, the electron avalanche also radiates an acoustic signal due to the pressure increase and heating with impact to the surrounding materials. This acoustic signal has a signal spectra in a range of some megahertz at its origin. But this acoustic signal also suffers from the fact that the signal strength method with piezo sensors on the transformer tank strongly depends on the travel path and the materials involved. Thus, the strength of acoustic signals can't be correlated with the amount of discharge, and acoustic signals are typically only used for location of PD sources within the transformer. Here we will now take a short overview how the different signal types look like. First, we have here the electrical pulse traveling over conductor to the measuring point, looking quite clean. Compared to this, the radiated pulse into oil picked up with an antenna is looking rather frayed. And here you see the acoustic signals received by a piezo sender on the tank wall. For the oscilloscope shot showing the acoustic signal, it's worth to mention that the electric PD pulse has been used as reference for triggering. While this electric trigger travels more or less with the speed of light, the acoustic sound waves travel roughly with a speed of 1200 to 1600 meters per second in oil. Therefore, depending on the distance of the sensor to the PD origin, the travel times of the acoustic signals differ slightly. So here it's there, and here it's there. Again, partial discharges are measured in picocoulomb, and they are referred to as apparent charge, since there is maybe a deviation between the real discharge at the origin and the received one at the terminal. For a simple pass or fail testing, a part of a factory acceptance test, the shown meter view is sufficient. Compared to the meter view, the early scope view showing the PD distribution over the last voltage cycle gives already limited analysis capabilities. The last picture shows the current common phase-resolved PD pattern, giving in-depth research capabilities. For instance, this phase-resolved PD pattern, short PRPD, is not only clearly indicating that the discharges are created by gas bubbles. Compared to the same PD defects shown as a scope, there it's harder to see. You can also count how many bubbles you have. So 1, 2, 3, 4, 5, 6, I think there's a 7th, and so on. So after giving this short overview about the behavior of partial discharge and transformer, let's come now to the ICMsystem itself. The multi-channel version of the ICMsystem has been developed with focus on PD testing of power and distribution transformers. First, we will give a short overview of the features of the instrument itself before coming to the other part of the measurement chain together with the software. The ICMsystem is an advanced state-of-the-art PD and tangents delta measurement system with high-end signal pre- and post-processing, simultaneous real-time acquisitions on up to 10 input channels, and integrated acoustic PD location functions. It's able to perform measurements under AC and DC voltage, includes an oscilloscope, and optionally the spectrum analyzer. So, of course, the PD measurement circuits of the ICMsystem fully comply with the IEC 60270, and you have the built-in oscilloscope has a maximum sampling rate of up to 100 megasamples. The optional spectrum analysis can measure from 0 to 10 megahertz with a bandwidth of either 9 or 300 kilohertz. Both bandwidths opt for the option to perform IEC-compliant measurements when choosing a proper center frequency. Furthermore, the spectrum option includes the IIV measurements according to CISPRE and NEMA fully parallel with PD measurements. After presentation of the instrument, we will now come to the measurement chain. The measurement chain looks like following. The standard decoupling unit uses either a measuring impedance connected to a bushing test tab or a coupling capacitor. However, there are cases where also a current transformer may aid the conventional PD testing, either by being used for gating or for decoupling the neutral or similar. Directly behind the decoupling unit, the preamplifier is connected. This preamplifier does obviously an early signal amplification together with an impedance conversion from the high input impedance of 10 kilo ohms down to the 50 ohms. This way, we can spare the need for fiber optic transmission as basic noise suppression technique. The preamplifier is then connected to the instrument themselves, so the ICMsystem. The ICMsystem is available as half 19-inch version for up to 4 channels and as a full 19-inch system for up to 10 channels. So how does the minimum configuration for power transformers look like now? The minimum configuration for power transformers resembles the requirement to measure up to 6 bushings in parallel to comply with the IEC 60763. So the 19-inch acquisition units, the 6 acquisition channels, preamplifiers, and quadrupoles together with one PD calibrator is needed. Beyond this, the full configuration adds a spectrum analyzer option and the smart trigger for enhanced acoustic location. Furthermore, this configuration considers measuring the tertiary using coupling capacitors as well as a possible available neutral. The minimum configuration for distribution transformers requires only a measurement on 3 measurement channels, so the half 19-inch rack is sufficient together with the equipment needed to measure 3 channels in parallel. Since the acceptance limit for distribution transformers is 10 picocoulombs, so much stricter, we recommend to go for the CT100 anyways. Even if the signal is not gated but filtered later on, the CT100 is an effective tool to identify the origin of the disturbances, so the part of your facility which has to be separated by filtering later on. One important remark, please note if you plan to do acoustic measurements with acoustic fault location with the ICMsystem, you have to go for 4 acquisition channels to perform the triangulation. You will need 1 channel for the electrical trigger channel and 3 acquisition channels for receival of the acoustic signals. So, with description of the typical configurations, we will now come to the software. The ICMsystem software has 3 main display modes. The first mode is the single channel panel. When coming to transformer testing, the single channel panel is used before the actual test to adapt and optimize the settings to suit the situation in the test lab, and for in-depth research in case of a failed acceptance test. The second main display mode is the multi-channel panel, giving a comprehensive overview over the last PRPDs recorded on all channels. The third display mode is the acceptance test panel, which is an operation mode dedicated to perform factory acceptance test of transformers. Since we somehow have to hit a 1-hour limit, we just take a look at the single channel panel and the acceptance test panel, since basically the multi-channel panel is 10 times the PRPD on one screen. The single channel panel has in total 12 different display views and on top some additional pop-ups. We will restrain ourselves to the view used somewhere during a transformer factory acceptance test, either before for optimizing or afterwards for fault research. For historic reasons, the scope view has to be mentioned. With the early PD detectors, this view, either in this flat arrangement or as a lizard Jew display, was the first view giving not only the amplitude, but also the phase position. As mentioned previously, this view has been replaced by the PRPD or map display. The third view to mention is the spectrum view, which gives, together with the spectrum option, information about the partial discharger's frequency spectrum, here seen on the bottom. The last mode is the oscilloscope view, giving information about the pulse shape and in case of multiple signals about the different travel times. Again, here you see an electric trigger signal and here you see the acoustic signals. Unfortunately, in this screenshot, they are more or less arriving with at the same time. Only slight differences. The acceptance test panel has been developed with the intention to provide a mode dedicated to perform fast and easy transformer factory acceptance tests. So here the meters of all 10 channels are shown in parallel, 5 to the left and 5 to the right, while the center of the display mode offers 4 switchable views. The table view giving the recorded values during a factory acceptance test, a predefined strip chart view showing the measured voltages and PD values for the first 5 channels on top and for the second 5 channels on the bottom, and 2 live chart views. This first live chart views shows on the left the first 4 channels, the first 4 recorded PD values over time, and on the right the recorded voltages measured over time for the first 4 channels. However, those live chart views can be freely configured. For instance, the second live chart view shown is here giving only 2 graphs with the PD values of channel 5 on top and the PD values on channel 6 on the bottom and the voltages on the right side. So after the overview of the software, let's now take a look how to do a factory acceptance test, which often faces a major obstacle in the beginning. A common problem for any kind of PD measurement is picking up high frequent disturbances radiated by the surrounding equipment during the measurement. To understand why that's happening, it's helpful to consider the following points. The measuring impedance is close to the ground connection, either below the coupling capacitor or below the device under test. So it measures basically all HF signals picked up over the common ground. Second issue is, during construction of many transformer factories, PD measurements were either not considered at all or not common, which led to the fact that there's often no separated ground system for the HV laboratory. So high frequent disturbances created from machinery used for manufacturing affect the sensitivity of PD measurements. To cope with this problem, the signal-to-noise ratio within the allowed frequency range is examined and optimized by evaluating the noise floor for the available filter combination using a typical test circuit, including the device under test. So here one remark, common noise coupling into the measurement circuit is especially a problem when coming to factories which produce distribution transformers. The lab is usually simply a small separate area in the production, and beside that you have a much stricter acceptance limit of 10 picocoulombs, so you have even higher restrictions for your noise floor. The second point worthy to mention here is the fact that the shape and height of disturbances received may vary over the day, since again, depending on whether someone is welding or if a cherry picker is charging or a crane is moving or similar. If the engineers doing these measurements are not aware of the context, it may become hard to understand what's happening and why. This often leads to the conclusion that this PD thing is somewhat unpredictable, but usually it's not, it's just physics. So with the ICMsystem, noise optimization is done during calibration in map view. Here, a calibrator is used to inject a known charge and one of the 3 lower available cutoffs and one of the upper cutoffs is chosen. Then a PRPD has to be started, and with a double click on the clearly visible calibrator pulse, the channel is calibrated. So afterwards, you save your calibration and you're more or less done. One remark here, this is a rather clear and fine calibration. Here you expect no difficulties later on. However, if you have a strongly fluctuating noise floor influencing your PD pulse, or if you see something that you inject a positive pulse and get a negative value, you can be sure that you have some oscillations and have to take care of them later on. Especially when coming to the factory acceptance test, we then recommend to do dedicated calibration for each of the maps individually. So how do you do the noise optimization? To optimize the signal to noise ratio, you now do a calibration for all 9 available filter combinations. With the 2015 amendment of the IEC 60-70, all of them are compliant to the standard. So here you see a calibration done from 40 to 600. While the PD pulse is here, the noise floor is somewhere roughly here, so 0.65 picocoulombs. Here you have a PD calibration where the noise floor has the same signal level, but the PD pulse is smaller, so the signal to noise ratio is worse. And the best calibration in this case was achieved with filter settings 42 to 800 kilohertz, since here again the noise floor has the same signal level, but the PD pulse is clearly stronger. So if these combinations don't yield in the desired result, the spectrum option would offer further possible measurement frequencies. Another popular way to deal with the surrounding noise is pulse discrimination on the detector side, but here the IEC 60-70 is quite strict. The summarized signal suppression by window gating, polarity discrimination, or similar should not exceed 2% of the measuring times. So if you use a pulse discrimination in one or another way, by gating, by blinding out pulses in certain frequency ranges or similar, you have to make sure that your detector does not exceed a gate time of 2% of your measurement time. Here is also one asterisk, so one remark. The total time for gated signals may be raised to 10% if it's clearly distinguishable that the interference comes from main side. However, this is often still not enough, considering the fact that common noise is normally random distributed over the complete voltage cycle. You see this also here, it's coming from everywhere, basically. In this case, we therefore recommend to go with physical filtering using HV or line filters, typically T filters for power transformers and pi filters for distribution class transformers. So after we have explained how to optimize the noise situation, at least roughly, we will now come to the induced voltage PD test. First, we will explain the different steps. The induced voltage PD test can be separated in 2 sections. The first, the preparation and calibration without voltage, and afterwards the test itself. So you start, you connect the instrument and the accessories, you perform the PD calibration. If required, you do the RV calibration. Then you perform a linearity test for both. You disconnect all calibrators, and then you secure the HV test area. With securing the HV test area, the preparation has been done. So now coming to the test itself, you start the record. You apply voltage and trigger the values for PD and voltage until the elevated voltage level at the predefined levels in the standards. For 1 hour or the 180-second period, you set the auto trigger. You wait till the voltage curve specified for your test specimen is complete, and you create the factory acceptance test report afterwards. So when testing power transformers, the connections look like shown. The measuring impedance is connected to the test tab. The measuring impedance delivered then 2 signals. The PD signal, which is connected via a short cable to a preamplifier, and the amplified signal is then connected to the ICM system together with the divided voltage signal. Here's a second cable, also shown here, directly fed to the ICM system. The divided voltage signal used is used for measuring the test voltage and for synchronizing the PRPD. Important remark here, without proper synchronization, any PRPD recorded during the measurement itself is useless. So this voltage signal has to be connected as well. For distribution transformers, the connection is similar, only the measuring impedance is usually replaced by a coupling capacitor, shown here, with measuring impedance built in. Again, you see here the preamplifier, and then you go to the instrument. Again, the preamplifier to the PD inputs, the voltage signals to the voltage inputs. And of course, the ICM system is fully computer controlled. Now we do the calibration for transformer testing. For transformer testing, we introduce the cross-coupling matrix. There you connect the calibrator as shown. You inject the specified calibration value. You open the calibration panel. Here you see the uncalibrated value, 425 he's stating. However, we are injecting 500 picocoulomb as shown. We calibrate with the specified charge. And then we open the linearity test panel to perform the linearity test. Here you already see that the linearity test for verification of the calibration has been done, and for 200 picocoulombs. Usual values for the linearity test is half of the calibration or acceptance limit and double the acceptance limit. Afterwards, you repeat with the next phase until we are done with all phases. So when the calibration is done, the cross-coupling matrix gives detailed information about the signal propagation between the different decoupling points. What can be learned when we take a look at this? If you have PD close to the bushing, so at the far outest point on phase 1U, you see at least 12% of the signal also on the phase 1V. This ratio increases with PD deeper in phase 1U, since it's then stronger cross-coupling. Especially as shown here, it's worth to mention that depending on the transformer type, the neutral shows a rather strong cross-coupling. So despite the fact that it does not have to be tested if you have already the 6 bushings, here you would have them as 1U to 1V and 2U to W, sorry, not V. It still can provide valuable information later on. Considering the structure of a transformer, this is also logical that the cross-coupling is rather strong. The bushing with the test tab is on one end of the winding, and the neutral or the start point is the other end of the winding. As mentioned beforehand, in some cases, dedicated PRPD calibration for every channel may be necessary. This you normally see with the map calibration on the first channel for each side. And if the signal is there, rather clear and clearly visible as shown in the screenshots in the slides before. So this is basically the PD calibration. Now let's go with the RIV calibration. Here we will start with the CISPRO compliant calibration, since this is executed nearly the same way as the PD calibration. However, instead of a pulse, a sine wave with a specified frequency is injected. So here you connect a calibrator type Cal3D similar to the PD calibration. You open the calibration panel. We are injecting 100 microvolts, but we have not calibrated yet, so we get anything, but we clearly see the signal. We check the calibrator and detector frequency, they have to match. The CISPRO recommends 0.5 megahertz, but also allows 1 megahertz. Again, we inject the specified calibration value. Now we calibrate with the amplitude. We open the linearity test panel. Here we do the same linearity test as with the PD measurement. So first the verification of the calibration, then half of the calibration value, and then double. And then we repeat with the next phase. While the preceding CISPRO calibration is very similar to a PD calibration, the NEMA compliant calibration consists of 2 steps. The adjustment procedure estimating the attenuation given by the connections and cables from the quadrupole to the measurement device, shown here, and estimation of the signal distribution between reference channel and device under test in the second step. Important, for a valid adjustment step, the reference channel has to be wired exactly with the same cable type and length as the measurement channels later on. Another thing is, during the adjustment, the measurement channel is not connected. So, and The remaining things are rather similar to the SysPro. You open the calibration panel, you set the cal mode to NEMA. You first check again calibrator and detector frequency. The NEMA says 1 megahertz. You inject the specified calibration value. Again, we are going for 100 microvolts. We adjust the reference channel first. Then you connect the measurement channel and you check both signal levels. You should see a small drop on the reference channel. And then you calibrate. And again, you can now do the linearity test. However, here we will sphere the picture. And we repeat with the next phase sample. When the linearity test and the calibration are done, you disconnect everything, clean the HV area, and secure it. Now you are ready to do the factory acceptance test. Therefore, you start the record, you switch on HV, and for the values requested up to the elevated voltage step, you can either trigger them manually, as shown. So here we have manual trigger mode, and then you simply press a button, giving you the values. Or you set the auto trigger with a short period, and then just take a look at this column. You remove the not needed values afterwards. So when reaching the 1 hour period or 180 seconds, you switch to the auto trigger and you set the according trigger interval. I think it's 5 minutes for the IEC 627 compliant power transformer measurement and 30 seconds, if I'm recalling it correct, for the distribution transformers. In case of PD, you can take a click on one of these small buttons and record a PD in the background. One option is that you just do the complete discussion afterwards, or you can activate a pop-up directly giving you the measured phase resolved PD pattern. Then you continue the voltage curve until the specified curve for your specimen is complete. You stop and save the measurement. And in case of a successful measurement, you now come to the FAT report, so the factory acceptances report later on. Where is it? In case of a past PD test, the only thing left is preparing the documentation. Here are two options. First, more or less a raw data export into Word, HTML, or text files. This way, you can easily import the measurement data into your own report templates. The second option is a ready-to-go report. Here you can edit header and footer. You see it here, you can adjust the entries. Also, you can change the logo. And the content itself is comprehensive and neat report about the performed test, giving the cross-coupling metrics, the values in the table, and also some predefined strip charts. So in case of a successful factory acceptance test, you are now done. However, in case of a failed test, let's take a look what could have happened within your transformer. There are 4 different possible sources which could create PD signals within a transformer: sharp points and particles, surface and tracking discharges, fiber bridges in oil, gas inclusions, so voids, bubbles in oil and solid, or delaminations between paper and within paper and solid materials. And last, the humidity, which could create indirect PD source, or is an indirect PD source. So each of these different failure types create usually a characteristic appearance within the PRPD. For instance, here you see a PRPD of a sharp edge. A sharp edge state starts in the negative maximum, and with increasing voltage, you will see the streamer discharge in the positive half. As soon as you see the streamer discharges starting, you should be careful, since then a breakdown is rather close. This is a typical PRPD of a void type defect. The void is always following the sine wave. So here you see it, and here you see it following roughly the voltage sign. However, please be careful. The shape of a PRPD also depends on the position within the transformer, more precise on the chance to get a free electron to start the discharge avalanche, either by photons or by ionizations. For instance, this is also the PRPD of a void, but with a high availability of starting electrons. So for well-founded PRPD interpretation, at least a rough understanding of the physical processes behind the partial discharge charges are really helpful. Besides giving information about the type of problems, the PRPD gives also information about the rough position of the recorded defect. Assuming the shown circuit is used, so that with the device under test directly connected to ground and the measuring impedance between coupling capacitor and common ground, the following behavior can be observed. PD in the test sample branch has a negative polarity in the first half cycle and a positive polarity in the second half cycle. Compared to this PD in the coupling capacitor branch, you see there you have positive polarity in the first half cycle and negative in the second half cycle. Just in case, the shown defect is a surface discharge, most likely a crack in epoxy resin due to a thread which has been tightened with excessive torque. As seen before, the polarity of the PD pulses recorded already give important information about their origin within the test circuit. Also, often the recorded amplitudes are already sufficient to estimate the originating phase. Either the originating phase directly shows the highest amplitude, or a comparison of the signal distribution using the cross-coupling matrix may solve the riddle. However, especially for PD deeper within a winding, a cross-coupled signal may have a similar amplitude as the signal on the originating phase, which leads to a 50-50 chance to be correct. In this case, the shapes of the recorded pattern may help. Here you see at least two voids. However, these two voids are not following the sine wave. So this led to the conclusion that these signals must be cross-coupled signals. This is a signal recorded on the originating phase. Here you see the voids following the sine wave again. However, you can observe that both patterns have a similar amplitude. So here you have roughly 180 picocoulombs. Here you maybe have 200, maybe also 190. While the strongest signal was recorded on the neutral with over 1.6 nanocoulombs. This led to the conclusion that the imperfection must be quite deep within the winding. Usually, these techniques are already sufficient to estimate the position within the transformer, at least close enough to do acoustic fault location. In case PRPD and amplitudes during the three-phase excitation do not succeed, we will shortly address additional in-depth research options. In case of PD defects which show a somehow unclear phase positions, so not clearly cross-coupled, energizing only one phase may help. First of all, obviously, if you energize a healthy phase, the defect won't be shown anymore. Second, with energizing only one phase, you can clarify if the problem is either between the energized phase and ground, then the phase position will stay the same. On the other hand, if the problem occurs between two phases, the phase position will change with a single phase excitation. So here you see that the sign is slightly on a different position. And just in case, this was a problem between an HV winding and a tertiary. Furthermore, and if available and possible, single phase excitation with elevated neutral helps to estimate the defect position within the winding. Due to the elevated neutral, the voltage drop across the suspicious winding is reduced from your peak to zero down to from your peak to only a third of your peak. So if your inception voltage stays then the same, the defect must be quite close to the bushing. If the inception voltage lowers, it's PD deeper within the winding. Additional research in time domain can give valuable information about the transmission bar. With respect to the influence of impedance changes and so on during the travel path, a signal traveling a conductor is rather sharp and clean, here shown in the first graph. while a radiated signal, which is picked up somewhere, is usually stronger oscillating. Last but not least, the spectrum analysis can also give information about the signal position. A missing high-frequency component is a strong indicator for a signal originated deep within the transformer, since the higher frequency components are stronger suffering under attenuation effects, as stated before, than the lower frequencies. Once the position has been estimated roughly enough, the remaining for the research can be done by using the acoustics. Here we take advantage of the fact that the electron avalanche of partial discharges causes local heating and a rapid local pressure increase. In liquids, this pressure increase causes a spherical pressure wave front if there are no solid obstacles close to it, or a longitudinal wavefront in case of a problem between solid materials. Solid materials offer, beside the pressure wave, additionally the shear or transverse wave traveling between their surfaces, to say it like this. The transmission velocity in liquids has typically a negative temperature coefficient. So with increasing temperature, the signals are radiated slower in oil. The travel times in oil are, for instance, around 1400 meters per second at 20 degrees Celsius and 1200 meters per second at 80 degrees. Last but not least, the pressure wave in solid materials travels with approximately double the speed of the shear wave. For steel, the shear wave is usually in a region of 3000 meters per second, while the pressure wave travels with roughly 6000 meters. So, coming to the triangulation itself, the textbook triangulation would placing one sensor on the front, one on the top, and one on the side of the transformer, and solve the created equation system for the origin. However, a real-life transformer has an interior consisting of a lot of different components and materials, which may block transmission paths, have different transmission speeds, and similar. So you cannot assume a uniform transmission. Furthermore, the tank wall is not a thin membrane. The tank wall is an additional transmission path for a pressure wave created by the arriving wave traveling through oil, together with the shear wave created by the, let's call it, impact of the wave. Additionally, the so-called inflex also reflects a part of the signal again. Long story in short, this leads to multiple transmission paths. To cope with this, we transferred this textbook triangulation into an iterative one by solving flat problems. So first, 3 sensors are placed in a horizontal line to narrow down the X position of the issue. Using the travel time of the different signals, the software calculates the travel distances. The intersection of these distances is then giving the improved position. So the result of this horizontal measurement is used to place the sensors vertically on the tank wall to estimate the Y position in a similar way. Afterwards, this newly estimated Y position can be used to improve the horizontal triangulation again. This can be iterated until the desired position is reached. With the ICMsystem, acoustic fault locations can be done simply by using RS75 and replacing the RPR1 with the RPR1D or the RPR1G. The RPR1D and G deliver the phantom supplies need to use the RS75. Furthermore, we offer a dedicated fault location software, which uses the data provided by the ICMsystem's oscilloscope as basis for the triangulation, here done horizontally, vertically, and then shows the result directly in a model of the research transformer. Here the bigger dot, or here enlarge. So with a short overview over doing acoustic fault location, we are now more or less on the end of the presentation. So thank you for your attention.
Yeah, thank you very much, Daniel. At this time, the presentation portion of the webinar is officially concluded. All right, we'll now take several minutes to answer your questions. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those that are leaving, when you close the webinar window, a survey should pop up on the screen, and we would greatly appreciate if you could take a couple of minutes to provide your feedback so that we can continue to improve upon future webinars. On the survey, there's also a field where you can request a demo or quote on any Megger products. A copy of the presentation along with a link to the video recording of the webinar will be emailed to everyone in about a week. So you can also view video recordings of the previous webinars on our website at www.us.megger.com/webinars. And please don't forget to register for next month's webinar. That will be offline PD testing of rotating machines using ICMFlex and ICMsystem. And the presenter will, again, thank you all for attending. Please take some time to answer the survey. The survey will also include a field for you to request a quote or a demo if you're interested. Thank you again, and yeah, have a great rest of the week.